In this video, we're going to take a look at the mean value theorem. And to do that, let's first just picture a function that we see that at some point there are two different values here and here, that for those two given x values a and b, we see that our function is equal to the same thing. They have the same y value. So f of a is equal to f of b. Well, in order for that to happen, and if this is a continuous function, there has to be some point where we get this turnaround, where we go from increasing to decreasing. And we know when we have that turnaround, that's when we have a slope of 0. And so this is kind of significant here, and not coincidental, in that we see that there is a point where the slope is 0. So this brings us to Rolle's theorem, where if we have a function that is continuous on a closed interval and differentiable on the open interval, meaning we don't really care if we're differentiable at the endpoints, just main thing is we're differentiable everywhere in between. So we're continuous and we're smooth. If there's some point where f of a is equal to f of b, then there has to be a point c such that f prime of c is equal to 0, and c is somewhere in between a and b. Where Rolle's theorem does not hold up is if we have a function that's not continuous, like we have here in our first example, or if we have a function that is not differentiable, like at that corner. So the function has to be both continuous and differentiable in order for Rolle's theorem to work. So if we have the same y value on the endpoints, then there has to be some point at which our derivative is equal to 0, as long as the function is both continuous and differentiable. Where this can give us some help is that if we have this function y equals x cubed minus 7x squared plus 10x, we see that, hey, this is a cubic. We would expect to have 3 zeros of this function. And so if there are 3 zeros, then that means we're going to cross the x-axis 3 times. Well, that's going to be 2 separate intervals on which Rolle's theorem can apply. So from what we have over here at 0, we also have another one here at 2 and another one at 5. And so we see that, well, since we have the same y value on this interval, there has to be somewhere where our slope is 0. And we have the same y values on this interval, there has to be another point. Now we can find those points by setting the derivative equal to 0 and solving, but this theorem doesn't so much help us find the points as let us know that those points exist and that there has to be some point. Though Rolle's theorem doesn't seem to be all that significant, if we take a step back from that, we can kind of start to build the mean value theorem here, in that let's just look at the secant line, any secant line. So not just a horizontal secant line, but any secant line on an interval from A to B. And if we draw that secant line, we can find that slope based on our secant slope equation. And we can draw a tangent line using the tangent slope using f prime of some value at any point in between A and B. And so what we see is that there's some point, in what is pictured here, we see that this tangent line is parallel to our secant line. And so we see at this particular point C, our tangent slope is equal to our secant slope on the interval. And so once again, that might not seem all that significant until you look at it from the other end to see that if we have a continuous function f on the closed interval and is differentiable on the open interval, so once again, that same premise has to be there. We have to have a continuous function on the closed interval and differentiable on the open interval. Then there is at least one point, there has to be some point C in A and B such that the secant slope on the interval is equal to that tangent slope. And so the mean value theorem tells us that the mean value, what does the word mean tell us here? We're talking about the average value. How do we calculate average value in calculus? We use the secant slope. So this is why this is called the mean value theorem, or oftentimes we'll say it's MVT. Okay, the mean value theorem tells us that there has to be some point at where our instantaneous rate of change is equivalent to the average rate of change over that interval, as long as we have a continuous function on that interval. Continuous and differentiable on the interval. This oftentimes is used in data in that if we have two data points here and here, and we know that the function is changing in between those two data points, we don't know how exactly it's changing. But based on these two data points, we can find an average rate of change from one point to the next using our secant slope. And so we know that that secant slope has to equal our tangent slope at some point. Now, we don't know exactly where that point may be if we just have two data points, but we can be guaranteed that there was some point on this graph where the instantaneous rate of change was equal to a negative 8.1 degrees Celsius per kilometer. And we can be guaranteed that by the mean value theorem. And that's one of the most significant guarantees that the mean value theorem gives us. Let's say we have this function here, y equals 2x cubed minus 3x plus 1 on the interval from negative 2 to 2. Now let's first ask ourselves, is this a continuous function? Yes, it is continuous because it's a polynomial. And is it differentiable on that function? Yes, it is differentiable. If we take its derivative, it's just going to be a polynomial once again, and that's going to be defined everywhere. So this is continuous and differentiable on the closed and open interval respectively. And so we want to find, is there a point where on this graph does our tangent slope equal our secant slope? Or where do we have an instantaneous rate of change that is equivalent to our average rate of change? So first off, let's find our average rate of change. Let's find our secant slope. So we can find our secant slope by plugging in f of 2 minus f of negative 2 all over 2 minus a negative 2. And so by plugging in 2, we get 2 cubed, which is 8 times 2 is 16, minus 6 is 10, plus 1 is 11. And then we want to subtract, plugging in negative 2 cubed is negative 8, which gives us a negative 16, plus 6 is negative 10, plus 1 is a negative 9. And we want to divide all of that by 4. And so this shows us that our secant slope is equal to 5. So we want to know, well, first off, the mean value theorem tells us that there has to be at least one point where our tangent slope is equal to 5. So let's find where is f prime of x equal to 5. So where do we have f prime equal to 5? So to do that, we need the derivative. So let's take the derivative. So f prime of x here, which, if you want to call it y prime, that's fine either way. That's going to equal the 6x squared minus 3. Okay, now when is that equal to 5? Well, that's going to be when 6x squared is equal to 8, and when x squared is equal to 4/3. And so this is when x is equal to plus or minus the square root of 4/3, or we can say 2 over radical 3. If you want to change this to 2 radical 3 over 3, that's fine, but we know that this is going to happen at positive 2 over radical 3 and negative 2 over radical 3. So we see that there's 2 points in which our instantaneous rate of change is equal to our average rate of change. Now, if we look at this graphically, we see that those points do in fact happen. We know right here and right here, those points satisfy the mean value theorem in that our average rate of change is equal to our instantaneous rate of change. Now, all of the calculus we did there, nothing there is new. The new part here is the mean value theorem guarantees that that has to be the case. There has to be some point in which our instantaneous rate of change is equal to the average rate of change.